All right, in this video, we're going to talk about section 2.5, dealing with limits at infinity. Now, in the last section, we talked about infinite limits, where we found out whether the limit as x approaches some finite number for a function approaches either positive infinity or negative infinity, both on the left side of that value or to the right side of that value. All right, so now we're going to look at limits when x approaches infinity. Okay. So here, limits at infinity as opposed to infinite limits occur when the independent variable becomes large in magnitude. For this reason, limits at infinity determine what is called the end behavior of a function. An application of these limits is to determine whether a system, such as an ecosystem or a large oscillating structure, reaches a steady state as time increases. Okay, so now we're going to focus on first limits at infinity and also horizontal asymptotes. Okay, so here is the definition. If f of x becomes arbitrarily close to a finite number L for all sufficiently large and positive x, then we write this: the limit as x approaches infinity of the function f of x equals to L. And I might need to write this so that way you can see it. So limit as x approaches infinity of the function f of x equals L. Okay. Now, in this case, the line y is equal to L is the horizontal asymptote of the function f. If the limit is at negative infinity, that's the limit as x approaches negative infinity of f of x equals m, it's defined analogously. And in this case, the horizontal asymptote will be y is equal to m. So we do have the limit as x approaches negative infinity of f of x equaling to m. So here's an illustration of that here. Here we've got a function y equal f of x. So as x gets bigger and bigger and bigger, that means as x approaches infinity, then that means that the graph of this function f of x gets closer and closer to some limiting value, which we're going to call L. Will it ever reach that value? Probably not, but it's just going to get closer and closer and closer to L as we let x approach infinity. And now for negative infinity, in other words, if we let x approach negative infinity, as we let x get smaller and smaller and smaller, then what's going to happen here is that this will get closer and closer to some limiting value, which we're going to call, I'm going to draw a vertical dotted line here. Okay. I'm going to let that be m in this case. So that means as x approaches negative infinity going in this direction, the graph of y equal f of x here gets closer and closer to some limiting value m. Okay. And that's what we call the limit as x approaches negative infinity of f of x. That's equal to some value m. Okay, now we're going to determine the limits of rational functions as x approaches infinity, both positive and negative. To determine the limits of rational functions, we divide both the numerator and denominator by x to the n, where n is the largest power appearing in the denominator. This forces the terms corresponding to the lower powers of x to approach 0 in the limit. And then we apply this rule. That's the limit as x approaches plus or minus infinity of 1 over x to the n, or we can write that as a limit as x approaches plus or minus of infinity of x to the negative n. That's going to equal 0. Okay. So what we're saying here is this: as we let x get bigger and bigger and bigger, or if we let x get smaller and smaller and smaller, 1 over x to whatever the power of n is, it's going to get closer and closer to 0. And pretty much you can verify something like that on a graphing calculator. Like, let's say, if I go to y equal to, let's say I want to do 1 over x squared. So it'll be 1 divided by x d theta for the x and then squared. If I do a zoom 6 here, you can see as we let x get bigger and bigger and bigger, this graph gets closer and closer to 0. Or if we let x get smaller and smaller and smaller, that graph will get closer and closer to 0. The graph of 1 over x gets closer and closer to 0 as we let x get smaller or as we let x get bigger. Okay, that's what we mean by that. All right, so now on the next page. In the first example, we're going to evaluate the following limits. And in this case here, we're going to evaluate the limit as x approaches infinity of 6 plus 7 over x squared. Now here we're going to apply some of the limit laws here. Notice I have a sum, a limit of a sum. I can write that as the sum of their individual limits. So I can write this as the limit as x approaches infinity of 6 plus the limit as x approaches infinity of 7 over x squared. Now here the limit of a constant is that constant. So the limit as x approaches infinity of 6 is 6. And then plus, if I have the limit as x approaches infinity of 7 over x squared, that 7 is a constant. I can pull the constant in front of the limit. So it'll be 7 times the limit as x approaches infinity of 1 divided by x squared. Now, as you're going to see here, based on that rule that I just showed you, as we take the limit as x approaches infinity, then 1 over x squared will be getting closer and closer to 0. Okay, as x approaches infinity, 1 over x squared gets closer and closer to 0 based on that rule that I just showed you. Okay, so this is going to be 6 times, well, 0 times 7 is 0, and 6 plus 0 is 6. So the limit as x approaches infinity of the quantity 6 plus 7 over x squared would be just 6. Okay. All right, here's another example. Let's say we had this. We want to evaluate the following limit. The limit as x approaches infinity of 8 plus 6x plus 6x cubed divided by x cubed. Okay, we want to find the limit of that. Okay, so here's what we're going to do. To calculate that, what we do here is we divide both the numerator and the denominator by x to the n, where n is the largest power appearing in the denominator. So the only largest power that appears in the denominator for x is going to be the 3. So it'll be x cubed. That's x cubed. So here we're going to divide the numerator. Each term in the numerator will be divided by x cubed. So that means I'm going to bring up the limit as x approaches infinity of that 8 will be divided by x cubed plus 6x will be divided by x cubed plus 6x cubed will be divided by x cubed. All that's divided by the denominator of x cubed will also be divided by x cubed. Here I'm taking the highest power in the denominator and dividing each and every term in the numerator and the denominator by the largest power in that denominator. Now let's simplify this. The limit as x approaches infinity of this will remain as 8 over x cubed plus 6x divided by x cubed. I'll be left with just 6 over x squared plus 6x cubed divided by x cubed would just be 6 divided by x cubed divided by itself is 1. All right. Now let's try to take the limit of each of these individual terms here. Like for the limit as x approaches infinity of 8 over x cubed. As x approaches infinity, what's going to happen here is 8 over x cubed will be approaching 0. And for the 6 over x squared, as we let x approach infinity, that 6 over x squared will be approaching 0. So I'm going to be left in the numerator with 0 plus 0 plus 6, which will end up being 6, and divided by the limit of a constant will be a constant. So I'm going to have a 1 in the denominator. So 6 divided by 1 is 6. So the limit as x approaches infinity of 8 plus 6x plus 6x cubed all divided by x cubed will end up being 6. Okay. Right here is another example of finding the limit as x approaches infinity of negative 6x squared divided by, 6x squared, negative 6x squared minus 4x plus 15 divided by negative 16x squared minus 6x plus 18. So here we're going to use that rule of dividing each and every term in the numerator and the denominator by the largest power in the denominator. The largest power in the denominator is x squared. So we're going to be dividing each and every term in the numerator and the denominator by x squared. So I'm going to bring over the limit as x approaches infinity of, let's see, I'm going to use brackets here. Negative 6x squared will be divided by x squared. Minus 4x will be divided by x squared. Plus 15 will be divided by x squared. The denominator, negative 16x squared, will be divided by x squared. Minus 6x will be divided by x squared. Plus 18 is also going to be divided by x squared. So every term in the numerator and the denominator is being divided by the largest power in the denominator. Okay, now if I simplify this, bring down the limit as x approaches infinity, negative 6x squared divided by x squared will be negative 6. Minus 4x divided by x squared will be 4 over x, because one of the x's divides out, plus 15 over x squared. Divided by negative 16x squared divided by x squared will be negative 16. Minus 6x divided by x squared will be 6 over x squared. Plus, this will remain as 18 over x squared. All right, so with our constants, the limit of a constant is a constant in this numerator. For 4 over x minus 4 over x, if I take the limit as x approaches infinity, minus 4 over x goes to 0. And if x goes to infinity, 15 over x squared will also go to 0. And then the minus 16, well, the limit of a constant is a constant, so it would be negative 16. Now for the minus 6x squared, as I let x approach infinity, this term goes to 0. And for the 18 over x squared, if I let x approach 0, that term goes to 0. So this is what I'm going to be left with, just negative 6 over 16. Negative 6 over negative 16. And if I reduce, I'll divide the numerator and the denominator by 2. And negative divided by negative is a positive. So this will end up being, in simplest form, 3/8. Okay. All right, and here's one more of these. Let's say I want to find the limit of 9x cubed minus 4x squared plus 3x divided by negative x cubed minus 2x plus 7. And here the limit will be as x approaches infinity. All right, in this case here, the highest exponent in the denominator will be 3x to the third. So I'm going to be dividing each and every term in the numerator and the denominator by x cubed. Okay, don't worry about the negative sign in front of the x cubed. So then negative 9x cubed will be divided by x cubed, minus 4x squared will be divided by x cubed, plus the 3x will be divided by x cubed. Then the denominator, well, negative x cubed will be divided by x cubed, minus 2x will be divided by x cubed. Because x cubed is the highest exponent there in the denominator, and then the 7 will be divided by x cubed. Now the limit as x approaches infinity. Now let's simplify all of this. Negative 9x cubed divided by x cubed, that's negative 9, minus 4x squared divided by x cubed. That would be 4 over x. I will be left with an x in the denominator, plus 3x divided by x cubed. Well, one of the x's will divide out. I'll be left with a 3 in the numerator and an x squared in the denominator. Now my denominator, negative x cubed divided by x cubed, negative 1, minus 2x divided by x cubed. That would be a 2 in the numerator and x squared in the denominator. Then plus 7 over x cubed. Nothing to divide out. Now, as we know, or should know, that the limit of our constants will be a constant. Now, as x approaches infinity, 4 over x goes to 0. And as x approaches infinity, 3 over x x squared also will go to 0. Now for the 2 over x squared, if I take the limit as x approaches infinity, then 2 over x squared, its limit goes to 0. And the same with the 7 over x cubed as I let x approach infinity. It's going to go to 0. So now we're going to end up with just -9 divided by -1, which ends up being 9. Okay. So that's how we take limits here as we let x approach infinity. All right, now we'll look at infinite limits at infinity. Infinite limits at infinity. And in this case here, it is possible for a limit to be both an infinite limit and a limit at infinity. This type of limit occurs if f of x becomes arbitrarily large in magnitude as x becomes arbitrarily large in magnitude. Such a limit is called an infinite limit at infinity and is illustrated in this picture right here for the function of f of x equals to x cubed. Okay, so here's the graph of the function f of x equals to x cubed and what it looks like. Now, as you can see here, as x approaches infinity going in this direction, you're going to see what's happening here is shooting off to positive infinity. So here, the limit as x approaches infinity of the function f of x is infinity. And not only that, we can also talk about negative infinity as well. Because as x approaches negative infinity, that's going in this direction, that means your x values are getting smaller and smaller and smaller. The values of f of x is going downward. It's getting smaller and smaller and smaller. It's heading towards negative infinity. So for this, the limit as x approaches, say, negative infinity of the function f of x, which is of course equal to x cubed, that would be negative infinity. Okay. All right, on the next page is the definition of infinite limits at infinity. All right, and it states if f of x becomes arbitrarily large, as x becomes arbitrarily large, then we write that as the limit as x approaches infinity of f of x equals infinity. And I might need to fill that in. A limit as x approaches infinity of f of x is infinity. Okay. The limits, which are these three, the limit as x approaches infinity of f of x equals negative infinity, and the limit as x approaches negative infinity of f of x is equal to infinity, and also the limit as x approaches negative infinity of f of x equals negative infinity are defined similarly. Okay, so here's a couple of graphs that illustrate just that. Infinite limits at infinity tells us about the behavior of the polynomials for large magnitude values of x. First, consider the power functions of f of x equal to x to the n, where n is a positive integer. The one on the left, as you can see, shows that when n is even, the limit as x approaches infinity of x to the power of n is going to go to positive infinity. In this case right here, function where the power is even is this: y is equal to x squared. Here's what that looks like. So as you can see here, with n being greater than 0 and it's even, the limit as x approaches infinity of x to the power of n shoots off to positive infinity. And the limit as x approaches plus or minus infinity for x to the n equals to infinity. And that's just both plus or minus for an even function. Now for an odd function, what's going to happen here is this: the limit as x approaches positive infinity of x to the n goes to positive infinity, and the limit as x approaches negative infinity of x to the n goes to negative infinity. So here, n is going to be a positive number and it's odd, like y is equal to x cubed. When you go to positive infinity on a function with an odd exponent, as we approach positive infinity, it shoots off to positive infinity. But for x going to negative infinity, that function shoots off to negative infinity. Okay. So here it follows that reciprocals of power functions, like f of x equals to 1 over x to the n, or we can write it as x to the negative n, where n is a positive integer, behave as follows. The limit as x approaches infinity of 1 over x to the n will go to 0. And the same holds true for the limit as x approaches negative infinity of 1 over x to the n. It too goes off to 0, or approaches 0. Don't never get to 0, but it just get closer and closer to 0. Right, next is Theorem 2.6, dealing with limits at infinity of powers and polynomials. All right, here we're going to let n be a positive integer and let p be the polynomial p of x equals a to the n x to the n plus a to the n minus 1 x to the n minus 1, and so on, all the way down to a sub 2x squared plus a sub 1x plus a sub 0, where a sub n is not equal to 0. Okay, here's some rules here. The limit as x approaches plus or minus infinity of x to the n will be equal to infinity. And that is when your n, that's the exponent here, is even. Like x squared, x to the 4th, x to the 6th. Your exponent has to be to an even power. Now, when we're dealing with an odd power like x cubed or x to the 5th, the limit as x approaches infinity of x to the n will go to infinity, whereas the limit as x approaches negative infinity of x to the n will go to negative infinity. Okay, and then number 3, the limit as x approaches plus or minus infinity of 1 over x to the n would go to 0. Okay, we've already saw that before. And 1 over x to the n is the same as x to the negative n, if you wrote it as a negative exponent. Okay, now here's number 4. The limit as x approaches plus or minus infinity of p of x, which is the limit as x approaches plus or minus infinity of a sub n x to the n, will be equal to plus or minus infinity. And that depends upon the degree of the polynomial and the sign of the leading coefficient, a sub n. So here with this rule, you're going to be focusing on just the leading term, a sub n as x to the n. A sub n, that's the coefficient of the variable to the highest power. If you remember from college algebra, a sub n is the leading coefficient That's the coefficient of the variable to the highest power. You have to look at the sign. That sign will tell you if it's going to go to positive infinity or negative infinity. Okay, now let's look at some examples of just that using these 4 rules in this theorem. Starting with example 5, determine the following limit. Let's say I want to find the limit as x approaches negative infinity of 2x to the 25th power. Okay, in this case here, notice I have a coefficient in front of the x to the 25th. That can go in front of the limit using the constant multiple rule. So this will be 2 times the limit as x approaches negative infinity of x to the 25th. So now I'm going to have 2 times. Now, let's think about this for a moment. Here, our exponent is odd. So as we let x approach negative infinity, x to the 25th will be approaching negative infinity. Okay, so I'm using rule number 2 here. I'll bring that down so that way you can see it. Here, the limit as x approaches negative infinity of x to the n, and if n is odd, in this case, it's going to be negative because I'm letting x approach negative infinity. And then 2 times negative infinity will just simply be negative infinity. So the limit as x approaches negative infinity of 2x to the 25th power will be negative infinity. Okay. All right, let's look at this example here, example 6. Here I want to find the limit of the polynomial p of x as x approaches infinity. Okay, so we got p of x is equal to 2x to the 5th minus 7x to the 4th plus 1. So I'm finding the limit as x approaches infinity. The polynomial p of x. Now with that, we only focus on the leading term when it's written in descending powers. Here, the leading term in this case will be 2x to the 5th. So I'm just going to focus on that. So the limit as x approaches infinity of 2x to the 5th. Okay. So in this case here, I'm using number 4, where the polynomial function p of x, I just focus on just a leading term, a sub n x to the n. Now I need to look at the degree of the polynomial and the sign. Here the degree is the highest exponent in that polynomial function is a 5, and it's odd. And I'm approaching infinity. So that means here the limit, and you know what, I can write this by pulling the 2 on the outside using the constant multiple rule. So it'll be 2 times the limit as x approaches infinity of x to the 5th. Then that'll be 2 times, well, as x approaches infinity, here x to the 5th will be going to positive infinity because it's an odd number. So that means since it's going to infinity, that means it's going to be approaching positive infinity as well. 2 times infinity is infinity. So that's the answer right there. The limit as x approaches infinity of the polynomial function p of x will be infinity. All right, now the next example, example 7, is finding the limit of the polynomial function p of x as x approaches negative infinity. So this time, we're taking the limit as x approaches negative infinity of p of x. So with a polynomial function like this, all we do there is just look at the leading term here. In this case is 3x to the 7th. And also you want to make sure that your polynomial is in descending powers from the highest exponent to the smallest. Okay, so 3x to the 7th is the leading term. All right, so now I'm going to use the constant multiple rule and pull the 3 out in front of the limit as x approaches negative infinity of x to the 7th. Here, my exponent is 7, is odd. So if I'm letting x approach negative infinity, then that means x to the negative 7, x to the 7 will have to approach negative infinity. And of course, 3 times negative infinity is negative infinity. So the limit as x approaches negative infinity of p of x will be negative infinity. Okay. All right, on the next page is in behavior. In behavior. Now, what in behavior is just the behavior of the graph of the function on the left side and on the right side. All right. The behavior of polynomials as x approaches plus or minus infinity is an example of what is often called in behavior. Having treated polynomials, we now turn to the in behavior of rational, algebraic, and transcendental functions. Okay. So here's the theorem 2.7, dealing with in behavior and asymptotes of rational functions. Okay. Mainly, we're looking at horizontal asymptotes. If you've had college algebra before, you should be familiar with the term horizontal asymptote and what it looks like. If you were to graph it, it's the horizontal line that crosses the y-axis. All right, so suppose f of x is equal to p of x divided by q of x is a rational function where p of x is all of this, written out as a polynomial function, and q of x is another polynomial function. Now in p of x, they use a's as their coefficients, and q of x, they're using the b's as their coefficients. Now here, the restriction is that a sub m and b sub n do not equal 0. And when we determine asymptotes, we always look at the highest exponent in the numerator and compare that to the highest exponent in the denominator. And these are the conditions here. If m is less than n, if m is less than n, the highest exponent in the numerator is less than the highest exponent in the denominator, then the limit as x approaches plus or minus infinity of the function f of x will equal 0. And the equation y equals 0 is the horizontal asymptote of the function f of x. Now in college algebra, you were told that if m was less than n, then you were just given this right here, that y equals 0. But here, when we take the limits, you're going to find out that the equation y equals 0 will be the horizontal asymptote. And then in B, if m equals n, meaning the highest exponent in the numerator equals the highest exponent in the denominator, that means the limit as x approaches plus or minus infinity of f of x will be your leading coefficients in the numerator, a sub m, and in the denominator, b sub n. A sub m divided by b sub n. And y equals the quotient of the leading coefficients a sub n, a sub m, and b sub n. That would be your horizontal asymptote of the function. Now, in part C, if m is greater than n, that means that the highest exponent in the numerator is greater than the highest exponent in the denominator, then when you take the limit as x approaches plus or minus infinity of f of x, is going to be equal to infinity or negative infinity. And that function will have no horizontal asymptote. Now in part D, let's say your m, that's the highest exponent in the numerator, is one more than the highest exponent in the denominator, that's the n. M is one more than n. Then when you take the limit as x approaches plus or minus infinity of f of x, it's going to equal to either infinity or negative infinity. And that function will not have a horizontal asymptote. However, the function will have what they call a slant asymptote. And then part E, assuming that f of x is in reduced form. That means p and q, the polynomial function p of x and the polynomial function q of x, share no common factors. And vertical asymptotes occur at the zeros of q. So that means when you're trying to find a vertical asymptote, you take whatever q of x is, set it equal to 0. And you want to make sure that you have no common factors. You want to divide those out before you identify your vertical asymptotes. Okay. Now let's apply this theorem with these examples. In example 8, here I want to evaluate the limit as x approaches infinity of f of x and the limit as x approaches negative infinity of f of x for the following rational function. Then give the horizontal asymptote of the function f, if any. So in this case here, I got f of x is equal to 7x divided by 49x plus 3. And of course, f of x is equal to 7x divided by 49x plus 3. Let's identify the n and the m in that problem. Well, notice your n is the highest exponent in the numerator, that's the 1. Your m is the highest exponent in the denominator, that's also 1. And as you can see here, that n does equal to m. Okay, so n does equal to m, that's right here. And now we can take the limit as x approaches infinity. The limit as x approaches infinity. Well, I don't need to write that. I already have that right here anyway. So let me wipe that out. So let's go from here. We can do this, divide the numerator and the denominator by the highest exponent in the denominator. So this is 7x over x. The denominator 49x divided by x plus 3 over x. And then 7x divided by x, that's 7 over 49, because the x is divided out, then plus 3 over x. Now, if I let x go approach infinity, then 3 over x goes to 0. So that means I'm going to have, in this case, 7 over 49. And 7 over 49 reduces to 1/7. So as we let x go to positive infinity, the f of x approaches 1/7. Now I need to look at the limit as x approaches negative infinity of that same function. And I'll write that as 7x over 49x plus 3. Well, what's going to happen here is this: if I go through that process of dividing each and every term by x, guess what? As I let x approach negative infinity, if I let x approach negative infinity, I'm going to get this 7 over 49 plus 3 over x, but 3 over x will go to 0 as we let x approach infinity. So I'm going to end up with still 7 over 49, which will be 1/7. Okay, so at positive infinity, the limit of that function goes to 1/7, and at negative infinity, the limit of that function is also going to 1/7. So that tells me what my horizontal asymptote is. So my horizontal asymptote is the equation y is equal to 1/7. So y equal 1/7 is the horizontal asymptote. Okay. All right, now let's look at example 9 on the next page. Evaluating the limit as x approaches infinity of f of x and the limit as x approaches negative infinity of f of x for the following rational function, use infinity or negative infinity where appropriate. Then give the horizontal asymptote of the function f, if there is one. So here we got f of x equal to 6x squared minus 7x plus 8 divided by 2x squared plus 1. And in this case here, if I identify the m and the n, the m is the highest exponent in the numerator, that's 2. Your n is the highest exponent in the denominator, that's also going to be 2. So here 2 is equal to 2, m is equal to n. So what I'll do here is take the limit as x approaches positive infinity of f of x. And of course, the limit as x approaches infinity, and f of x is at 6x squared minus 7x plus 8 divided by 2x squared plus 1. Okay, so in this case here, using that rule in Theorem 2.7 Part B, the limit of this will be going towards these leading coefficients here in the numerator and the denominator. The limit of this will be approaching 6 over the limit as x approaches infinity. This denominator will be getting closer and closer to 2. I just look at the leading coefficients here, 6 over 2, which is 3. So as x approaches infinity, this function gets closer and closer to 3. Now let's try finding the limit as x approaches negative infinity of that same function, 6x squared minus 7x plus 8 over 2x squared plus 1. Of course, our exponents, the highest exponent in the numerator and the denominator are the same. We can just look at the leading coefficients here, the 6 and the 2. So it'd just be 6 over 2, which will be 3. Okay, so as we let x approach infinity, the limit of that function went to 3. And as we let x approach negative infinity, the limit of that same function also approached 3. So my horizontal asymptote is the equation y is equal to 3. Okay. All right, now let's say in this example number 10, I had a function like this. And I want to evaluate the limit as x approaches infinity of f of x and the limit as x approaches negative infinity of f of x for the following rational function. Use infinity or negative infinity where appropriate, and then give the horizontal asymptote of f if there is one. Okay. So in this case here, we got f of x is equal to 43 x to the 6 plus 2x squared divided by 16x to the 5th minus 4x. Okay. Now, I'm going to identify the m and the n. The m is the highest exponent in that numerator, that's 6. And the n is the highest exponent. The n is the highest exponent in the denominator, that will be 5. Compare m and n. You can see m is greater than n. So that means here, when we take the limit as x approaches infinity of 43x to the 6 plus 2x squared divided by 16x to the 5th minus 4x squared. I mean, just 4x, not 4x squared. Now, if I did this, what I can do there is, divide each and every term in the numerator and the denominator by the highest exponent of that denominator, which is, of course, x to the 5th. So here the limit as x approaches infinity of, 43x to the 6 will be divided by, let's just say x to the 5th, plus 2x squared will be divided by x to the 5th, divided by 16x to the 5th is divided by x to the 5th, minus 4x divided by x to the 5th. So here I'm dividing by each and every term by x to the 5th, which is the highest exponent in the denominator. Now let's simplify this. Bring down the limit as x approaches infinity of x to the 6 divided by x to the 5th, which is the x. So I'm going to have 43x minus the 2. If I divide x squared by x to the 5th, I'll have an x cubed in the denominator over 16x to the 5th divided by x to the 5th, that's 16, minus 4x divided by x to the 5th. I'll have a 4 in the numerator, but x to the 4th in the denominator. Now, what's going to happen here with these two terms here, as we let x go to infinity, these two will be going to 0. So the only thing that I will have left And I have to bring down the limit as x approaches infinity of 43x divided by 16. Well, that's just a linear function. So if I let x go to infinity, then that means 43x over 16 will have to go to infinity. Has to. Okay. Now, what about when we let x go to negative infinity? So to the right of that, I'm going to do the limit as x approaches negative infinity of that same function, f of x, which is 43 x to the 16th minus 2, well, plus 2x squared, all divided by 16x to the 5th minus 4x. Now, if I go through that process of dividing each and every term by x to the 5th, I'm going to get the same thing, 43x over 16. So let me bring down the limit as x approaches infinity of 43x over 16. And that should be as x approaches negative infinity. Because we already found the limit as x approaches positive infinity. But what about negative infinity? Okay. So as x gets smaller and smaller and smaller, this is getting smaller and smaller and smaller right here. So it's heading towards negative infinity. All right, so if you compare the limit as x approaches infinity, it's going to positive infinity. But for the limit as x approaches negative infinity, it's going to negative infinity. It's going to two different places there. That's two different places. So that means that the graph of this function that we're dealing with has no horizontal asymptote. And if you look at something else here, notice that your m is one more than n. 6 is one more than 5. So not only do you not have a horizontal asymptote, you actually have what they call a slant asymptote. Because notice the highest exponent in the numerator is one more than the highest exponent in the denominator. Okay. All right. Now let's end this video with in behavior of transcendental functions. And basically, when we're talking about transcendental functions, it's going to be functions like e to the x, e to the negative x, and the natural log of x, or ln of x. The end behavior for e to the x and e to the negative x on this interval, negative infinity to infinity, and for ln of x on only this restricted interval from 0 to infinity. And we don't include 0, so it's an open interval here. And it is given by the following limits. Here the limit is x approaches infinity of e to the x is going to be equal to infinity, and the limit as x approaches negative infinity of e to the x is 0. And then the next line, the limit as x approaches infinity of e to the negative x, that's going to be going to 0. And for the limit as x approaches negative infinity of e to the negative x, that would go to infinity. And then for this one, the limit as x approaches 0 from the right. Notice 0 from the right, not from the left, because I'm going to tell you this. You cannot take the natural log of 0, nor can you take the natural log of a negative number. So it has to be x approaching 0 from the right of the natural log of x. That's going to be negative infinity. And then as we let x approach positive infinity of the natural log of x, that would be infinity. Okay, so here the natural log is very restricted because we can't take the natural log of 0 and we cannot take the natural log of a negative number. All right, take a look at example 11 using that theorem. All right, here I want to determine the end behavior of the following transcendental function by evaluating appropriate limits, then provide a simple sketch of the associated graph showing asymptotes if they exist. Okay. In this case here, we got f of x is equal to 3 times e to the negative x. So we're going to try to find the limit, or, well, to determine the end behavior, we have to find the limit as x approaches infinity. And this is of 3e to the negative x. Well, let's pull the 3 out in front using the constant multiple rule. So it'll be 3 times the limit as x approaches infinity of e to the negative x. So this will be 3 times. I'm going to pull this down to show you when we let x approach infinity, e to the x, e to the negative x, here it is right here. As we let x approach infinity, e to the negative x goes to 0. So we're going to have 3 times 0, which is 0. And let's take a look at the limit as x approaches negative infinity of 3 e to the negative x. Again, I'm going to pull the 3 in front of the limit as x approaches negative infinity of e to the negative x. And in this case here, as we let x approach negative infinity, the limit of e to the negative x is this, infinity. So 3 times infinity ends up being infinity. Okay. All right, and finally, example 12. Determine the end behavior of the following transcendental function by evaluating appropriate limits, then provide a simple sketch of the associated graph showing asymptotes if they exist. Okay. Once I finish this, I'll do the graphs here for examples 11 and 12. All right, so let's say we got the function f of x is equal to 2 plus ln of x. 2 plus ln of x. All right, in this case here, we need to do the limit as x approaches 0 from the right of the function f of x. Okay, and that's going to be the limit as x approaches 0 from the right. And I'm getting that from right here because I'm dealing with ln of x. So I'm starting with the limit as x approaches 0 from the right of ln of x, because there is ln of x in that problem. So and that's of, let's see, f of x is a 2 plus ln of x. All right, I have a limit of a sum. I can write that as the sum of their individual limits. So I can write this as a limit as x approaches 0 from the right of 2 plus the limit as x approaches 0 from the right of ln of x. Well, regardless if it's going to the right or to the left, the limit of a constant is a constant. So that limit as x approaches 0 from the right of 2 will be 2 plus using the rule for the limit as x approaches 0 from the right of ln of x, that's going to be, in this case, negative infinity. So 2 plus negative infinity, well, that's just going to go to negative infinity anyway. So the limit as x approaches 0 from the right, 2 plus ln of x will be negative infinity. And now we look at the limit as x approaches infinity. Of f of x. So look at the limit as x approaches infinity of 2 plus ln of x. So in this case here, I'm using this one right here. As x approaches infinity, I'm finding the limit of the natural log of x. And this has the natural log in it. So now, the limit of a sum, again, will be the sum of the individual limits. So it'll be the limit as x approaches infinity of 2 plus the limit as x approaches infinity of ln of x. Well, the limit of a constant is a constant, so the limit of 2 as x approaches infinity will be 2 plus the limit as x approaches infinity of ln of x. Let's go back up here. Here's the limit as x approaches infinity of ln of x. That's this, infinity. And 2 plus infinity ends up being infinity. Okay. Now, if we want to provide a simple sketch, this is what we can do here. I'm going to bring up my calculator here. I'm going to go to y equal 2, and then type in that function 2 plus, and then press the ln key, and then press the xc theta for the x. And then I'm going to do, let's say, zoom 6. Okay, pretty much that's what the graph looks like. Or if you want to do this, I can do zoom. I'm going to probably do zoom in. There we go. There's a better graph. But pretty much you can see what's happening here. As we let x approach 0 from the right, coming in this way, this graph is falling downward to negative infinity. And as we let x get bigger and bigger and bigger, you're going to see that this is just shooting off to positive infinity. It's not going to a specified value. Okay, now let me go back to example 11, so that way you can see what that graph looks like. F of x equals 3 times e to the negative x. So I'm going to go to y equal 2, clear this equation out, type in 3. For the e, I have to do second ln for the e. Second and ln gives you the e, and press the negative key at the bottom, and then x. Okay, let me do zoom 6. Now, as you can see here, in this case, as we let x get bigger and bigger and bigger, what's happening here is that this graph is going to get closer and closer to 0. And I might want to do this zoom in, zoom 2. You can see that is, as we let x get bigger and bigger and bigger, this graph is getting closer and closer to 0, but it'll never hit 0. And I'm going to go back to zoom 6 to zoom out. Now, in this case here, as we let x approach infinity, as x get bigger and bigger and bigger, this is shooting off to positive infinity, as I have here. Okay. Okay, so that does conclude this video on section 2.5, dealing with limits at infinity. All right, feel free to contact me if you have any questions about any of the material presented in this video or any of the homework that's in my MATLAB.